All right. Thank you all for joining me. Thank you all for putting up with the confusing room changes, and I'm glad you all made it. In case you were confused, this is best practices in drone surveying. So we're going to be talking for the next couple of hours about drones, how to create surveys with them, how to do it right, how to save time, how to save money, and all of that. If you're not here about drones, well, stick around anyway. You might learn a thing or two. So, thank you for being here. My name's Logan Campbell. I am the founder and lead photogrammetrist at a company called Aerotos. And today, like I mentioned, we are talking about the best practices in drone surveying. And that means we're going to talk about a lot of things, actually. We're going to cover a whole lot in the world of drone surveying. I'm going to do my best over the next 2 hours to summarize for you really the last 8 years of knowledge about drone surveying. 8 years is not too long in the world of surveying, but in drones, it's ancient. For anyone that has been flying drones for 8 years, you know it's changed a whole heck of a lot, as has, more importantly, the workflows and the procedures and the software and technology to actually go from flying a drone into a final survey. And that means we're going to talk about what are some of the things that drones can do, but also, probably more importantly, what drones should do, because it doesn't always make business sense to fly a drone. Sometimes it does. We're going to talk about what the right drone is, a little bit about hardware, as well as where and how to fly, and what is becoming more and more the most difficult and time-consuming and expensive part is how to actually process the data. So we're going to cover all of that today. A little bit about me. I apologize, it's cut off. I'm, like I said, the CEO and lead photogrammetrist of Aerotos. We do data processing for land surveyors and civil engineers. Like I've said, we've been around for quite a long time in the world of drone surveying, at least. But that's what we do. We do data processing for land surveyors and civil engineers. That's all we do, which is why we've actually had the opportunity to learn all of this stuff. That we've worked with surveyors all across the country, tens of thousands of projects, every single drone you can possibly imagine, and a number of drones that we really shouldn't process data for either. We've seen all of that stuff too. So yeah, that's us. That's what we do. I will also point out, for anyone interested, there is an opportunity. I have contact information at the end if you want a copy of the slide deck or a video recording of this presentation. We are recording it so that you can have that later. All right, so what's my goal here today? I like being upfront with you guys so that you know exactly what I am talking about and what perspective I'm taking on all of this. My goal is to help you build a drone program that, number one, you will actually use. That means I'm not trying to say, buy a drone that looks cool, you can put a picture of it on your website that says, we fly drones, and then no one actually uses it. I want to help you build a drone program you will actually use. I want one that saves you time as well. Not a drone program where you could have hand topoed the entire site in 2 hours, or you take out the drone and it takes you 10 hours to actually make the whole thing work. That doesn't work for me. I'm not a big fan of science fair experiments. I'm a big fan of business and actually getting a drone program that works. That is my goal. And also gets you better data. The reason I put this all up as the theme is because the drone industry has a lot of really awesome technology. I'm a tech guy. I love drone technology. But the point of this talk is not for me to talk about all of the different lasers that are out there, the technology that it uses. It's about how to make a drone program that actually works for surveying. I'm going to say this a lot. There's so many technologies out there that maybe can do something, or they're really cool, or they're absolute cutting edge. And I generally stay away from that in a talk like this, because if you're on the cutting edge, you're going to get cut and you're going to bleed and it's going to hurt. And so this is about actually taking this from the coolest hand-built thing you've ever seen in the world to a work truck. My goal is to take drone surveying and make it boring, super boring, which is weird because I'm literally talking about flying robots with lasers attached to them. And my goal is to make it as boring as possible to make you money. All right, and the most important way to do that is actually going to be to avoid a lot of the common pitfalls in drone surveying. Again, I tell you all this up front so that you know when I'm talking about and getting deeper into the technology, why I care about these things and why this is so important. Things like not using the wrong tool for the job. For a class about drone surveying, I'm going to tell you a lot of different times when you shouldn't be using a drone because it is the wrong tool for the job. You guys know this as well. Not every site uses the exact same tools, the exact same workflow. Also, don't overspend on gear you don't need. Maybe you have a computer gamer in the office who says, "Hey, we really need this $25,000, NORAD grade processing PC," and I'm here to tell you, no, you don't. You don't need to overspend if you actually get good workflow. You don't need to buy the drone that could, fly for 48 hours at a time and has thermal vision because you're not doing thermal mapping. You don't need that. I'm trying to make you not overspend on the gear that you don't need. Also, don't spend too much time in the office. Another very common pitfall. People say, wow, look how quickly I was able to fly this site. Now here's 250 gigabytes of raw LiDAR data. Let's figure out what we can do with it. And it takes 80 man-hours of processing, and you're toast. And again, don't treat this like a research project. A drone program should not be a research project. You're not trying to figure out what you can do with drones. You're trying to get your survey done in the most accurate, highest quality, and most efficient way possible. So the way that people usually go through this drone surveying journey, and I know I've talked to a bunch of people in this room already, there are people that are all along the spectrum in terms of how much experience you have from drones, ranging from never flown them, my kid has one, to I've shot some photos, to I've got a team of 5 that works on nothing but drone data processing the whole time. And that's awesome. But usually, you can't really see these too well, but people start by buying a drone and just maybe taking basic photos and videos, something like that, document a site. Then they start throwing it into a software like Pix4D or a Drone Deploy and stitching it together into ortho photos so that you actually have a map. Then you start adding in your control points, maybe RTK data. You start geo-referencing it to really get higher accuracy when you're actually mapping this, extracting your data. Then you start working in 3D, DSMs, point clouds, extracting topo data. And then you kind of start getting it into CAD as well, clean CAD drawings, merging it in with all of your other data, with boundaries, with prior surveys, that sort of thing. And then finally getting it to your final survey deliverable, but at the absolute top is actually turning this into a repeatable workflow. And that's often the hardest part for most people. Most people, when they get a drone, they'll get a whole project from start to finish, and without having a clean workflow, it's all going to be a new process from start to finish every time. And that's not how you make a repeatable, high-quality drone program. To make it repeatable and high quality, you need to have that repeatable workflow, that defined workflow, defined processes to actually know what you're going to get and how to get there. And so this is at a very high level what a drone workflow really ought to look like. That means it starts with the first step is going to be mission planning, the kind of most boring, really simple, and really easy to forget thing that makes everything work better, so much better in the office. Mission planning is simple questions like, should you even fly a drone on this site? What altitude should you fly at? And where should I set control points? Or how many control points should I set? Pretty simple questions. If you're an experienced drone pilot, you probably know the answer to that. And if you're an experienced drone pilot, there's a good chance you've answered those questions wrong and it's come to bite you at some point in the past too, from collecting too much data or not having the right overlap or that sort of thing. So mission planning is kind of boring but pretty important. Then go through to the data collection side. That's actually in the field. The simplest part, I barely talk about it at all because flying a drone these days is so brain dead simple. You push go and it flies. If your flight operations are any more complex than that in the field, then talk to me afterwards because they should not be much more complex than that. The drones all run on autopilot. You shouldn't be using any sort of manual flight. You don't need to touch thumbsticks. You don't need any of that. It should be real simple in the field. Then we go through into point cloud processing. That's going to be whether it's with LiDAR, creating a LiDAR point cloud, or photogrammetry, creating your ortho photos, your DSMs, your point clouds, things like that. Going through that computer step is pretty important. Once you go through that and create all of your point clouds, what I often call the raw deliverables, the full resolution ones, then you want to verify accuracy. This is another often forgotten step that only takes a few minutes, but is really, really important because it keeps you from spending an enormous amount of time drafting on data that isn't accurate in the first place. We're talking about surveying for we're talking about drones for surveying here, not drones for cool pictures or for real estate photography. And that means accuracy is one of the most critical things about this. And so that's why accuracy verification, I'll go into the details of that quite a bit later today as well, but that's going to be a really, really important part about making sure that your data is super high quality. After that is line work drafting. That's where you go from 200 gigabytes of a point cloud that has a point for every single leaf on the tree down to an actual topo map, a tin surface, paint striping on the roads, parking lots, utilities, manholes, lampposts, all of that. That's what that line work drafting is, to actually extract that data and turn it into line work. And then lastly is CAD integration. That's where you bring it all into Civil 3D, presumably, or Carlson, or any of the other numerous softwares that are out there, but to actually get your final survey deliverable. Because at the end of the day, what my goal is not to talk about how cool drone technology is, it's to tell you how most efficiently to get to this, a final survey. Is it from a drone? Is it from the ground? Well, it might say that in the notes, but you really don't know. And the answer is probably a little bit of both. That drones are really great for topo, but they're not going to know boundary. So you shoot boundary on the ground, you put it all together. Some stuff you do on the ground, some stuff you do from the air. And the goal is to get to a survey as efficiently as possible. Because I don't know about you, but very, very few clients ever raise their hand and say, hi, I'd like a drone survey of my property done. And they say, I want a survey done. I want this data. You figure out how to use it. In the same way that, some clients might specify the tools needed, but it's up to you as a surveyor whether to use a GPS or a total station, or whether you're correcting based off of a network correction service, or you set up a base and do an Opus solution. There's so many ways to do it, but it's up to you to choose the right tool. And that's what this is about, is choosing the right tool to get that survey. And the drone is an excellent tool that should be in your toolbox, even though it's not right for everything. All right, so that's what I'm going to be covering, at least from a high level. But to start with, one of the most common questions is going to be, all right, what drone hardware should we talk about? Also, by the way, I like questions. Even though I'm kind of standing up here in this dark shaded corner, I actually want to be here and interact with you. If anyone has a question, feel free to raise your hand, throw something at me. That's my point of being here, is to actually answer your questions and teach you guys what I've learned. So when we're talking about hardware or anything, feel free to raise your hand and I'd be more than happy to help. All right, so talking about drone hardware first. First is my hardware methodology. To choose the right hardware is going to take a balance of three things, is what I always say. First off, it's going to be ease and reliability of use. Now, that's not usually the first thing that people think of when they think of hardware, but what we have found is that it is really, really important to have a drone that is easy to use. There are drones that are, like I mentioned, push button and it flies itself. And then there are drones that it takes 3 days of full-time on-site training just to learn how to fly the thing, because it is so ridiculously complex that it is challenging to set up. Or if it takes a team of 2 to actually fly the drone or bring it to a job site, that's a pain in the butt. I'm not saying that it can't get good data or that it's not a very high-quality piece of equipment. What I'm saying is, to make a drone program useful and save you money, you want to at least think about this as part of the comprehensive drone program, as part of what you are buying. Also, you do care about accuracy of the final data. Accuracy matters. Now, that is notably second in what I say, that accuracy matters to a point. And I'll talk about that a little bit later. But the best accuracy, you get seriously diminishing marginal returns. And then the third thing is actually going to be the total cost of ownership of the drone. Now, there are a couple things that other people still don't usually think of when they see a drone and say, hey, that drone's $35,000, that's expensive, but I can make it work. But when we say total cost of ownership, that means you should also count in the fact that there is a cost of the equipment, but also to operate it, how skilled a crew needs to be, how much training that person needs, how much time it's going to take to fly it and actually operate that drone, as well as the cost of data processing. So often overlooked when this drone might be simple, cheap, and photogrammetry only, and this one is LiDAR and it's better. They get the LiDAR drone and they realize that they're drowning themselves in data processing costs because it takes so much more time and computer power and servers and all of that to process. So when we evaluate drones, we look at all of these things holistically, because it really kind of has to check all of those boxes for us to recommend it as a good drone to buy. And I say this as someone that's processed so many thousands of data sets, that kind of ease and reliability of use really is the most, one of the most important things out there. Which leads me to the most common hardware pitfall. And I apologize to any drone hardware vendors in the room because this can sometimes get me in trouble with them. If I can give you one piece of advice when buying a drone, listen to me, waving my hand. One piece of advice when buying a drone. Do not ever buy a drone based purely on the tech specs. That is the most common thing. And especially, I say that again as someone who totally is a drone hardware geek. As someone that was into this 8 years ago when I was hand building and hand soldering a lot of my own drones, I love the technology. I want to look at the pulse rate of the LiDAR unit. I want to look at the angular precision of the IMU and what type of GPS antenna is on it, and it breaks, and I want to figure out which part of the software stack broke and blah, blah, blah. But I'm a geek, and I have put a significant portion of my life into this industry to figure it out. You probably shouldn't. If you want to, more power to you. I won't stop you. But don't buy a drone just based on the tech specs. I can tell you, again, from processing all of these different hardware drones out there, basically never has someone come and said, well, the data's not good because it only takes 400,000 pulses of LiDAR per second and mine does 600,000. That's not the difference between a good LiDAR project and a bad LiDAR project. A good LiDAR project is one that works, and a bad LiDAR one is one where a super complex drone didn't have exactly the right field set up, so it didn't log the RTK at the right clock base, and it won't set with the PPK so that you can't process the data at all, and then it's worthless. And that's why I say don't buy a drone on tech specs, because that is something that we see an awful lot, where the highest quality drones, without the exact right, perfect field workflow, have data that's going to require a field revisit. And that's what eats into your time, what eats into your profit margins, what eats into all of that. So you can buy a very high-end drone and make it work if you know what you're getting yourself into. That's my recommendation. Never buy it purely based on the tech specs. All right, so getting into some of the actual drones that are out there. There are generally two categories of drones. There's DJI, and then there's everyone else. Those are kind of the two categories. And even between these two categories, DJI makes up about 70% of the commercial drone market in terms of hardware. They are overwhelmingly more popular, but they're not universally the best. DJI is, they're gonna have one of the most simple workflows. They're going to be relatively cheap, very easy to use, and typically they have good, but not necessarily the best accuracy. But it also has some downsides. It is going to be Chinese made for a lot of people that work on government projects, especially. That may or may not be allowed. They don't have good support, and it's not going to be the most cutting, bleeding edge technology out there. The everyone else drones out there, of which there are a lot, and a lot of them are very good quality too. I shouldn't be talking too much trash on the everyone else drones out there, because a lot of them are very, very good. They are typically going to be more specialized to your need, usually made in part, if not in whole, in the US, better hardware support and much more cutting edge technology, but the downsides to those ones are going to be more complex field workflows, typically going to be considerably more expensive and usually require some sort of specialized training. So there are trade-offs to both of these things. There are absolutely companies successful with basically all drones out there, but these are just some of the trade-offs to be aware of when you are looking at potentially buying a drone. With DJI drones, I should update this because these are now, as of a few months ago, they have been updated. The entry levels are going to be about in the $5,000 range for a photogrammetry drone, no RTK. The kind of best overall middle ground one is now going to be what's called a Mavic 3 Enterprise RTK. That is going to be an RTK dual band GNSS enabled photogrammetry drone for, you're looking at about $10,000 to $12,000 all in with all of your accessories and batteries and cases and yada, yada, yada. That's one that we really like, as it's kind of one of our favorite overall drones because it's a really good balance of the right technology, the right cost, the right ease of use, the right transportability. It's the type of thing that if you ever worked with a big drone, they're bulky, they're intimidating, they're loud, they can even scare people on the ground. Versus a Mavic, once that's up at 200 feet, nobody in the air can hear it. You can just get your job done. It's easier to use and it's boring. Again, that's a big thing. It's weird that I'm excited about making stuff boring, but that literally is what my job is to make drones super duper boring. And then your kind of cutting edge on the DJI one is going to be your M300. That's going to be the one that then is LiDAR capable, or it can have a P1, which is a much larger specialized photogrammetry camera as well. considerably more expensive, but also going to be more capable and a little bit more of a pain in the butt to use. Biggest thing, I'll give you the cliff notes there. If you're working primarily in non-vegetated areas, so if you're doing parking lots, if you're doing strip malls, or if you're doing roadway corridors without a huge amount of vegetated areas, a Mavic 3E with photogrammetry is probably going to be your best bet. If you are doing a ton of projects in the woods where you need topo and there is a lot of tree cover and that sort of thing, then you need LiDAR and you should go with an M300 style one. Likewise, there are a couple of different airframe types out there. This is consolidated over the past few years. Typically, there's your small multi-rotors like the Phantom series of drones or the Mavic 3 Enterprise series of drones, which are really, really high quality. A lot of people say, well, it's so small and cheap, it can't be good for survey. You'd be wrong. They're actually really, really good as long as you know what they are good for. Your large multi-rotors, a lot harder to use, 3 feet in diameter. They're loud. Everyone around knows that that one's flying. And then there are fixed wings as well. These have really fallen out of favor the last couple of years, simply because the trade-offs, the reason you would buy a fixed wing is because you can cover a whole lot more land, a whole lot more area with them. But multi-rotors have become so much more efficient in terms of their battery life that typically a fixed wing, the benefits just aren't as big as they once were. If you have a fixed wing drone, they still work great. We love fixed wing drones. But probably those are going to be only for sites of, I would say, if you're doing a couple 100 acres for a single project site and you're doing that regularly, then you might consider a fixed wing. Otherwise, the versatility of the multi-rotors has led them to be much, much, much more popular in recent years, at least. I also want to talk about the GNSS or GPS processing for drones, because this is a really, really critical one to your workflow. This is also one that few people consider when they are in the buying process of the drone, but is among the more important in terms of the ease of processing, right? When I talk about that total cost of ownership, knowing what the right GPS processing workflow is. Now, if you work with GPS for survey, which I have to imagine the most of you do in some capacity or another, you know that there's a bunch of different ways that you can process GPS. You can process it just recording data, and you can post-process the whole thing. You can post-process it against a base that you brought yourself, or you can have that real-time connected. You can have a Wi-Fi signal that connects to a global Trimble network that then broadcasts the correction data direct to your rover. There are so many ways to do it, and the drone is exactly the same. You can either have no RTK on a drone at all on the lower end, which means all of your accuracy is going to be set from ground control points that you actually set. Set a bunch of targets. That is what gives you the accuracy for actually matching up the imagery in the model with the real world on the ground. Then there is PPK, which post-processing kinematic. You do it all after the fact. It's a very flexible workflow that can get you very good accuracy, but it sometimes is tricky because you have to process it all in the field. You don't have, you process it all in the office after you come back from the field. You don't necessarily know that it's going to be high accuracy until you come back and process it. And then there are two types of common real-time kinematic data. You can either use a local base station or NTRIP. And NTRIP is the processing workflow for basically streaming corrections over the internet. And to jump to the conclusion here, we really, really, really recommend whatever workflow you use with the drone, having a local base station to actually collect and correct your drone data. We don't like network correction because network correction is very good for a lot of ground surveying because you're holding the rod, and if you have a bad network connection, you just wait a couple more seconds. Or it takes 5 seconds and you can actually average those to get a good observation. Whereas a drone is moving at 30 feet per second, wildly kicking around. If you have long baseline distances, and when I say long baseline distances for a drone, that could be a couple of miles, is a little bit longer baseline distance than we love for how quickly those drones are moving. Longer baseline distances, anything other than absolutely perfect internet connection, and the connection drops and it kind of becomes not nearly as good. So we usually recommend bringing a local base station, and that could either be the one that came with the DJI drone is actually really good for these use cases. Not going to replace your Trimble or Leica equipment or anything like that, but it's really good for those use cases. Either way, we strongly recommend, if you are doing GNSS correction for your drones, to bring a local base station and use that. One of the other questions is, when talking about drones, is LiDAR or photogrammetry? I've already talked a fair amount about LiDAR and photogrammetry. LiDAR is definitely way more of a hot topic right now. Everyone's talking about LiDAR. It's kind of the newest thing that's only become affordable. Aerial LiDAR has only become affordable in the last year or two, whereas photogrammetry has become a little bit more boring and old hat. But I'm here to actually go for the old proven technology a little bit and say that you know, LiDAR is not about to eliminate photogrammetry. Photogrammetry is still really good in a lot of different circumstances. Biggest difference is with LiDAR, LiDAR gets you better coverage in vegetation. So this is a profile view of 2-point clouds. It's going to be, one is in photogrammetry, and the other, the kind of darker one, is real world colored. That's photogrammetry. And this one right here is going to be LiDAR. And what you can see is LiDAR actually gets you a much cleaner ground surface in vegetated areas, which is really great. You want that, especially if you're doing topo where there's plants. LiDAR is going to be your best bet. But photogrammetry's benefits is it is considerably faster of a workflow, of a processing workflow overall, which I'm going to cover after the break. I'll get into the office workflow, the data processing software, all of that good stuff. It is easier. It is actually more accurate on hardscape right now. A common misconception a lot of people have is that LiDAR is going to be more accurate than photogrammetry. And if you ever see a ground-based laser scanner, then yes, it is going to be more accurate because that's on the ground and typically only going, you know, a few dozen feet from the sensor. But once you stick a LiDAR unit in the air, you have it wiggling around, moving, vibrating, and it's 200, 300, 400 feet away from the target, it actually winds up being slightly less accurate on hardscape. So if you are doing a strip mall Alta survey, then photogrammetry is actually going to be faster, easier, more accurate, and cheaper. Remember I said I was going to talk about that a lot? Actually making this work for you? Instead of the really cool, big, heavy, expensive drone, you can buy the cheap, boring one that not a lot of people talk about and still get better accuracy. Yeah, I'm here to tell you, yes, photogrammetry is far from dead and far from being replaced by LiDAR. Like I said, LiDAR works best in vegetated areas. If you do have very dense tree cover and you need topo, LiDAR works well. But if you're doing baseball fields, football fields, strip malls, dirt piles, stock piles, anything like that, photogrammetry is going to typically be a better solution. I've already went over this a little bit, why you should not use LiDAR. It's pretty expensive. It's bulky and hard to use. It often takes more specialized training to fly the drone. But it does make sense, like I said, if you're doing topo, if you're doing vegetated areas. But most importantly, I think, is, again, good workflow is going to be what really makes the difference. One of my favorite things is that a lot of LiDAR drones nowadays, in fact, any of the ones that I would recommend, carry both LiDAR sensors and photogrammetry capable cameras in the same integrated payload and fly them in the same flight. And that means you can take that drone, you can fly it, and if you don't need LiDAR, we just don't touch the data. Not because it's not useful data, but because it's pretty expensive to process, or it's more expensive to process at least than photogrammetric data. So oftentimes people will fly a DJI-L1 or a GOQ LiDAR drone and process it in photogrammetry only, and that's perfectly acceptable and oftentimes a good workflow. But it's using those good workflows that really makes the difference, that makes you want to fly a drone. A good drone program shouldn't be one that you have to use. It's one that people, your survey crews, come in and fight in the morning for who can take the drone because it's going to make their life that much easier. That's where all of these workflows should come into play. I've talked about the DJI-L1 sensor a lot. This is what it looks like. The DJI-L1 sensor is DJI's LiDAR and photogrammetry combined sensor. And we actually really like it. Now, your total cost of the drone LiDAR sensor, its own base station, and all of the batteries and junk there is, it's actually come down recently. It's about $35,000 now, which is of course quite expensive, but in the realm of LiDAR-equipped tools, it's not that expensive at all. And these are your realistic accuracies on this. 0.2 of a foot vertical accuracy, with the LiDAR sensor and about 1/10 of a foot vertical accuracy with the photogrammetry sensor. And you'll notice LiDAR is worse there, which is what I've been talking about. But if you are using the LiDAR only in vegetated areas, then typically when you're doing a survey of 40 acres of woods or something, 2/10 of a foot vertical is pretty good when it's just leaves and trees and mulch and stuff on the ground. And photogrammetry on the hardscape gets you a good enough sensor. So this is actually our favorite LiDAR sensor out there. But like I mentioned before, our favorite overall drone for land surveying is going to be a photogrammetry only drone. Mavic 3 Enterprise RTK. It's cheap. This is becoming the workhorse drone for surveyors out there because it is cheap enough at, again, about $10,000, $12,000 all in, cheap enough to have one in every truck, fly a site when you need it, really easy, really unobtrusive, and very, very common. Quite frankly, super boring. Again, good thing for me. Now, if you do, like I said, do a lot of vegetation and topos in vegetated areas, then the best overall, our favorite, is going to be the DJI M300 with the L1 sensor. Those are our favorite drones. Those are the ones that we think and what we actually see lead to the most successful overall drone programs. All right, before going on, I'll take a pause. Any questions on drone hardware or anything like that? Yeah.
DJI is Chinese. What's the best non-Chinese?
What's the best non-Chinese drone? That is a great question. Some of it is, unfortunately, I hate that I have to answer it, how non-Chinese does it need to be? Because unfortunately, there are extremely few drones out there that are enough non-Chinese to be fully, I forget the compliance numbers, fully DoD compliant, that they could actually be used by US military applications. Even the non-Chinese ones, when they are drones like GeoQ makes some very high quality LiDAR drones that we really like, but a lot of them are based on, even parts of them are on DJI platform, but it's not a DJI sensor, it's a wholly different sensor that is good enough for a lot of applications. Then there is Micro Drones is another company that makes very high quality stuff, but it's very, very, very expensive and hard to use, but that's going to go a lot further in satisfying it. On the lower end, you can make do with an Autel drone. Autel, it's not going to be as good as the Mavic 3 Enterprise RTK, but it is passable, especially for smaller sites. If you're only doing 10, 20 acres, you can set a couple more control points to make up for the lower accuracy from the kind of RTK camera integration issues that are there. Yeah, no problem. Any other questions on hardware? Because I know that's often people's favorite topic. All right, moving on then to mission planning, which, as I mentioned before, this is the most boring, easiest to forget, and yet most important part. So I talk about mission planning. The most common workflow that we see in mission planning, and honestly this is true in data processing too, we see a lot of workflows from people that have drone programs. You start by flying the drone, and then you give the data to the drone guy, and eventually you make money with it, or at least that's the goal. This is what we see most of the time, and as you can imagine, I'm not particularly a fan of that, which is why there is mission planning. So what is mission planning? Why am I talking about it? Why is it not just fly the drone and then magic, magic, magic data? Well, mission planning is first asking, is this a good site for a drone? That's your quickest way to save money on a drone, is not use it when you're not actually going to use it. If it makes sense, if you're doing a half-acre site, then it probably doesn't make sense to fly the drone and process the data and run through photogrammetry and accuracy checks and then extract data and then combine it. Too many steps, too much workflow for a very small site, typically. Asking yourself photogrammetry or LiDAR, pretty simple question. I kind of already covered some of that. What altitude should I fly at? There's a trickier one that I'm going to cover in a second. What's the right overlap? How many ground control points should I set? How many targets? These are some of the questions that you should ask yourself in mission planning. An experienced drone pilot, this will take 30 seconds, but you still need to do it beforehand to make sure that you actually are set up for success. Why care about it? Well, it actually means it'll save you time overall. You set fewer control points, less ground surveying, shorter flight times, but most importantly is no field revisits. That's where time really gets eaten up. Time and cost is if you ever have to go back into the field again. whether it's shooting additional control or manually shooting something because your drone didn't get good data. That's where time gets eaten up and why mission planning is so important. But also, mission planning really kind of sneakily, it saves a lot of office time. If you collect the right data, then it gets processed faster. There is absolutely such a thing as too much data in this world, where just transferring it can take hours and processing it can take days. So it saves office time by having good mission planning. And it would also lead to fewer photogrammetry errors, a simpler overall workflow if you have good mission planning. What we have typically seen is, of all of the projects that come into us, about 2/3 of photogrammetry problems are caused by bad mission planning. It is not because, someone shot the drone. It is not because there was a car driving and it ran over your ground control points, although we see that sort of thing too. It's not because it started raining. It's because of poor mission planning. As far as asking what is a good project for a drone, what isn't a good project for a drone, here are some just kind of basic rules of thumb for what actually works for good and bad projects. Good projects are in the range of 1/2 an acre to about 500 acres. While that is a pretty big range, it is worth noting that those ones on the outer edges are, again, where you kind of make money and don't make money a lot of the times. If you're doing less than 1/2 an acre, there's a good chance it's better to do it on the ground. And if you're mapping more than 500 acres in a single project, there's a really good chance that a traditional manned aerialist is going to make a heck of a lot more sense. Drones are fantastic. Drones are cheap. If you're doing one of those projects where it's, hey, you got 10,000 acres where you need to cover, then yeah, getting a traditional aerialist with a plane is still going to be more cost effective than a drone. We have done huge, much bigger projects than that, but that's the point where you definitely ought to consider talking to a traditional aerialist to fly those bigger ones. Again, up to about 20 miles on linear missions, whether that's power line corridors, pipelines, roadways, highways, things like that. Great for topo, alta, planimetrics, volume calculations, and that sort of thing. Bad projects, like I said, are going to be very, very large projects. Extremely high accuracy. Extremely high, by my definition, is if it absolutely must be better than 1/10 of a foot, then the drone is probably not going to be the right tool for that. If you're shooting railways and the specs on the railway survey that the actual rail ties themselves needs to be accurate within like 3/100ths of a foot, you're not getting that with a drone. Get your total station and you're going to use that instead. Also, indoors underneath overhangs. Could a drone theoretically map inside of a room like this? Yes, but it's a terrible idea. Don't do it. And as well as significant details underneath trees. That's something to be aware of, right? LiDAR can see through the trees, or can penetrate the vegetation rather, to actually get good topo data. But if there's a manhole that is entirely visually obstructed by the trees, the LiDAR is not going to pick that up. The photogrammetry is not going to pick that up. You got to get that on the ground. Like I said, when picking LiDAR or photogrammetry, biggest consideration there is just vegetation. If there is vegetation that you can't see the ground from the air with a picture, then you're going to want LiDAR. If there's no vegetation, then you're going to want photogrammetry. Pretty simple as far as that goes. Of course, you do have to bake in the fact that LiDAR is a lot more expensive. Do you do enough vegetated projects to make that hardware investment worth it? All right. So now let's get into a little bit more about mission planning, which is going to be safety and airspace restrictions. Thankfully, this topic, which used to be a huge point of contention a couple of years ago, has really gotten settled. The FAA, for once, has done a fairly, well, I say for once, I like the FAA. They've done a decent job at actually keeping things safe and making them relatively easy. For those of you that have your Part 107 license, that's what the drone licensure is called, to be a quote-unquote drone pilot. I put that in air quotes because, again, you just push go. The drones fly themselves nowadays, which is great. You need to pass your Part 107, and they make you study charts like this about knowing your classifications between Class A, B, C, D, G, and E airspace and all of that good stuff. And I'm not here to tell you about that because you need to study. If you want to get your Part 107, you study for the test, take the test, and then forget everything the next day. That's the way that it works. But the most important way to think about it is that, honestly, the majority of airspace in the United States is actually open. In fact, 99% of the United States land area is Class G, uncontrolled airspace, no paperwork required whatsoever to fly in it. But many projects are going to be within heavily populated, controlled things, or even on airports themselves, or on federal prisons, or that sort of thing. It's a common misconception, but you can actually fly in all controlled airspace. It's just a matter of the right paperwork. We've actually helped a lot of our customers do surveys on airport runways themselves because they have to close the runway for a shorter amount of time to fly it with a drone than they do if you actually have someone on the runway with a survey rod or anything like that. So you actually can, it's just kind of amount of paperwork. In fact, it's one of my favorite stories. We did some of the most restricted airspace in the US is actually over federal prisons because so many people use drones to smuggle drugs and cell phones and stuff into the prisons. So we had a project site where we were talking, they were like, well, we need to do a survey of the whole prison, but they won't let us bring nails in. If we have to bring any equipment in, it's all like, needs to be tagged and brought in and out. This was actually where O.J. Simpson was living at the time too. But it actually took us about a month to get proper approval through the FAA, through the prison warden and all of that to get the site flown with the drone, and we did, and it saved them days of time and a huge amount of headache because they didn't have to bring in any nails or survey poles or anything into the prison yard. So you can fly in a lot of places. There's a system called Lance, which is an automated approval. You can actually get most things just approval on your phone with just a couple of taps or with an app, and manual authorizations for everything else. For those that are interested in the technical details, there's some things called waivers, some things called authorizations. I'm not going to go into it in too much depth, but if you do care about this, waivers are good, authorizations, avoid them unless it is absolutely necessary. Because yeah, flying drones in the real world, a lot of people will ask, oh, but what about 107 subsection 19 part 35B that says whatever? Realistically, flying drones in the real world, the FAA, first of all, there's no FAA police force. They don't have their own police. They're not actually out there looking to try and give you a speeding ticket on your drone, or if you fly at 402 feet when it says you can only fly at 400, no one's going to get you in trouble. The FAA, all they care about is protecting manned aircraft. As long as you're not an idiot, as long as you're not flying at the runway where you're not supposed to and overriding all of the warnings on your drone and trying to dodge in between, business jets, that'll get you in trouble. Or at least I'm from California, so we have wildfires all the time. The other no-no is interfering with firefighting aircraft. They get real angry about that. But outside of that, honestly, you're fine if you're operating responsibly. Use your good judgment and you'll be absolutely fine as far as the safety and kind of being a responsible drone operator goes. All right, next up on mission planning and drones is going to be talking about autopilot software. This is another topic that used to be bigger, but is becoming a lot less so now that most drones come with their own autopilot software. You don't have to choose an autopilot to go with your drone. All of that to say, thankfully, most autopilots have become extremely similar to one another. They have really converged into the same basic set of features, the same basic set of here are your mission planning types. You can fly lawnmower pattern, or you can fly a linear mission. Most of them have terrain awareness in there as well. Terrain awareness is where the drone actually tries to approximately track the land. So on projects with significant relief, usually more than 100 or 200 feet of elevation change, you might want to consider using terrain awareness so that the drone actually tracks up and down and gets more consistent imagery, more consistent accuracy, more consistent resolution over the entire site. It is a little bit more difficult to use, but most autopilots now, anything in the last year really should have terrain awareness as well. So continuing with this topic of mission planning, next up is going to be flight altitude, overlap, and accuracy. This is where the rubber meets the road for a lot of these real day-to-day projects. Everything else, once you kind of know it, it's not a big deal. This is the type of thing that you need to be aware of for day-to-day projects. So when I talk about accuracy, the number one thing to me is starting with your desired results. Start with the accuracy that you need or that you want for your project, and then go back from there. And that's because there's kind of a natural flow of what happens. When I hear someone say, I want the best accuracy possible, I say, great, go to NASA and better have a $100 million budget, because the best accuracy possible is going to be really, really expensive. Or other times, I'll even give a price quote. It's like, I want the best accuracy possible. I'm going to fly this at 50 feet. I'm going to set 1,000 ground control points. I'm like, okay, that's going to generate 450,000 photos, and to process it, will be many, many tens of thousands of dollars. And then they'll say, okay, maybe I don't want the best accuracy possible. I want good enough accuracy. So that's one thing. The best accuracy possible is typically not what you want, unless you're doing a research experiment, which I have mentioned before. I don't like research experiments. So don't go that. Same thing, just fly as low as you can so we don't miss anything. Well, that's going to cause problems too. Or even, just fly it first and we'll see what data we can get out of it. These are all things that we see fairly commonly. And what that leads to is if you want the best accuracy possible, that just means it's going to be extremely expensive. The hardware is going to be expensive, the processing is going to be expensive, the time in the field is going to be expensive. If you just fly as low as you can so that you don't miss anything, well, you're going to generate an insane amount of data, and your project is going to take weeks or months to complete when you could do it in a day. And if you just say, fly it first and we'll see what data we can get from it, then you'll probably wind up not using it at all. And the data will be ultimately useless because you gathered a whole bunch of data, but not the data that you actually needed to get something useful done. So start with your desired results. And typically that means start with the accuracy that we want. This table is calibrated so that it actually works with most drones that are out there in terms of what your flight altitude is, how much area you can cover per flight, and how many photos it'll take. So what you'll see is if you want 1/10 of a foot accuracy, typically 1/10 of a foot is very good, especially for like Alta surveys. You can cover about 10 to 15 acres per flight at 150 feet above ground, but if you were doing 100 acres at that altitude, it would generate 6,000 photos. Likewise, if you flew at 400 feet down here, that'll get you about 2/10 of a foot accuracy, and you can cover 50 acres per site and generate about 750 photos. So what does this tell me, at least? Well, if you were doing topo on 100 acres of dirt for maybe a newly graded subdivision or something like that, and you need 1-foot contours, well, fly it at 400 feet. Because you don't need that extra little bit of accuracy if you're doing 1-foot contours. If you are doing a as-built survey on a new restaurant on a couple of acres, well, if it's a couple of acres and you're doing an as-built survey, you want all those utilities and everything to be as tight as reasonably possible, then fly it at 150 feet, which is typically the lowest that we recommend flying. Because you're not flying 100 acres, you can get away with a little bit more data on that one and still process it in a reasonable amount of time. And for a lot of projects, honestly, 200 to 250 feet is really kind of the Goldilocks zone in terms of high enough quality data for almost all projects without wasting too much time in the field or generating too much data. So 250 feet is our recommended altitude, just kind of as a baseline. If you're just doing topo 1-foot contours, fly at 400. If you're doing something that you need real detail and a lot of hardscape and utilities, fly at 150. It rarely makes sense to ever fly below 150. Then it starts to suffer from what we call the drinking straw effect. It's like trying to survey through a drinking straw, that the footprint that the drone can see is just so small that you actually wind up getting worse accuracy once you start getting lower than 150 feet. So we don't recommend flying below 150 feet. As far as flight patterns go, there are a bunch of different flight patterns out there. Different service providers, different people recommend different ones. This is your single grid pattern, kind of lawnmower style, back and forth, boustrophodonic, if you're interested in that sort of applying scientific Greek words to everything. This is going to be the most common, and spoiler alert, what we recommend for most project sites. Double grid is also a thing. Now, this has been a controversial thing when I've said it in the past. I don't like double grid patterns. It generates twice as much data, and we've done a lot of research and accuracy studies on this, and it doesn't generate better accuracy. So it takes twice as many photos, takes twice as long in the field, and generates generates statistically identical accuracy results. I don't like why so many hardware providers keep pushing this because, well, I know why. It's because the hardware providers often don't have to process the data. They push that on you. When I see people fly double grid pattern, I just think it's too much. You don't need it. With good mission planning, you can get good accuracy with a single lawnmower as well. There are some edge cases if someone is thinking, but I need to map these deep ravines, I need these angles and blah, blah, blah. Yes, there absolutely are some edge cases. There are some, depending on LiDAR units, yeah, there are cases where that does make sense. But for the majority of projects, particularly photogrammetry projects, single grid is going to get you the same data in less time, or same quality, less time, easier to process, less money. There are also linear missions as well. Again, most modern autopilots have this, where if you are doing power line, pipeline, roadway corridors, anything like that, you draw a line and it flies a couple of flight lines up and back. We recommend a minimum of 3 flight lines for what it's worth. 2 or 1, technically possible, bad idea. And then obviously terrain awareness, which I've talked to as well, where you import a model of the Earth and it tries to follow that. I said this before, and I know I'm repeating some of these things, but that's because these are the ones that are the most common pitfalls that we see, so I'm trying to get the point across. There really is such a thing as too much data, right? Like, too much data takes so much time to process. There's this feeling sometimes in the era of big data that just collect more data because computers can process infinite data. Boy, drones with photo, video, and LiDAR can really show you that there are costs to that sort of data. There are costs associated with it. This isn't Google where it's just, here's $1 billion, have fun, who cares what the cost of the data is? We do. We care about the cost of the data. So don't fly lower than you need. Don't use LiDAR if you don't need it. You'll wind up drowning yourself in data, and it often winds up killing a drone program entirely, that you don't use the drone as much because you know how much of a pain in the butt it is to process the data because you didn't get everything right in the beginning. Next up is talking about overlap a little bit in mission planning. General recommendation, 75-75 for overlap on photogrammetry missions. Again, there's some wiggle room there. I'm not going to plant my flag on that one. But that works pretty well for modern digital photogrammetry. What is worth noting is there are huge differences in required overlap depending on the type of drone you're flying and, more importantly, what type of image sensor. And I say that because anyone that's worked with traditional aerial photogrammetry knows that overlap numbers are way, way, way lower than they are in drone photogrammetry. And that's for a couple of reasons. One, it's because the cameras were so much more high quality, that you had these perfectly calibrated metric cameras that would cover huge amounts of land with the right fiducial marks and all of the reports, and they're 200 megapixels and they're $1 million each. They're wonderful cameras, but because they're so high quality, you don't need as much overlap. With digital photogrammetry, when you are using a couple $100 camera attached to a couple $1,000 drone, more overlap is required to properly internally calibrate the camera on each individual flight so that you can actually get that high quality accuracy. And also, the biggest one, and this is where LiDAR is so much newer to the surveying industry, that this has not reached a level of consensus yet within the industry of what the right LiDAR overlap is. I can tell you a lot of LiDAR manufacturers recommend what I, as the data guy, considers way too low overlap, like 30% or something. That means each LiDAR swath, only 30% of it will overlap with the swath, the flight line next to it. While that's technically possible, what I've found is that actually increases the error rate of the overall point cloud, that whether the swaths don't agree perfectly, if there's a couple tenths of a foot disagreement there, or if your laser scanner isn't perfectly calibrated or that sort of thing. And also that means your photogrammetry overlap is going to be lower if you're flying it as well. It leads to a lot of requirements to refly the mission if you don't have high enough overlap. And I say that as someone that's just been beating the drum of collect less data for a while, but with LiDAR, I actually like leaning a little bit higher. I've seen the most success in the 55 to 60% overlap on LiDAR, which does collect a little bit more data, but leads to a much more reliable workflow so that you know you captured the right data and you don't need to go out and fly the job site again. Again, that's one where the industry is still kind of coming to terms with it. Some people recommend very low. And you can get away with low overlap if you have really, really, really tight procedures. But if you increase your overlap a little bit, it gives you some flexibility for something to not work quite right, for there to be a little bit of an error and not need a field revisit. Because that's so important to me. I don't like research projects. I like doing surveys in the real world, and things happen in the real world. someone kicks a tripod, a ground control point gets messed up. When someone threw a piece of equipment into the truck too hard and it's ever so slightly out of calibration, but you increase the overlap, it can actually still kind of bail you out in those circumstances. Nadir versus oblique imagery. This is another one. A lot of people like to set their drone's camera to slight off nadir or oblique, meaning that it's at an angle. Nadir means it's pointing straight down. We don't think there's much of a need for that, and in fact, we usually don't like it, because if you look, this is what kind of a grid pattern would look like from a nadir perspective. But from oblique, this one you can kind of see the horizon there. What you actually see is in the distance, these squares get smaller. They appear to be smaller. That's lower resolution. So people think by going oblique, it's going to increase your accuracy, but it actually often doesn't. By adding that angle, it's lowering your effective true ground sampling distance on average, because the closer to the horizon, the further away from the drone, the lower the actual resolution is on the ground. So we typically like nadir only single flight pattern paths when it comes to photogrammetry. I mean, admittedly, if you disagree with me, then you probably know enough that this isn't that important. But if you just want some general recommendations, that's what I would say is single flight pattern, 75-75 only overlap with nadir only images and no obliques. All right. Don't worry, we're getting through it. Planning GCPs, and then I'll get into the data processing part, which, you know, everyone's so excited about data processing too. But we have a break coming up in just a little bit. All right, so let's talk about planning for ground control points. First off, and even though I just said we're talking about ground control points, we're talking about GNSS corrections again, because that majorly influences how many ground control points that you need. These are some of the different GNSS correction processes. Like I said, either using a DJI base station, an existing third-party base station like a Trimble or Leica, or a network correction service. Or what's actually missing on this chart is the option for no RTK correction whatsoever, and using only on ground control. Generally speaking, in order, or rules of thumb here, if you do not have RTK at all, then you need 5 ground control points per flight battery. That means if it takes 2 flights to fly a site, then you would need 10 control points. If you are flying with some form of RTK, then we would say minimum of 3 control points on a project, plus an extra 1 for every extra flight battery we use. That's our kind of rule of thumb there. As far as which GNSS correction you're using, accuracy-wise, DJI base stations and third-party Trimble or Leica base stations will get you the exact same accuracy. They're streaming local low baseline distance corrections directly to the drone, or more specifically, usually it's by way of the controller and then to the drone, but they are streaming corrections, and those are going to be some of your highest quality accuracy. Network correction service, we recommend setting additional control points because network correction services just introduce more error into the drone. That's also one thing. Usually these RTK systems are very, very, very good at predicting their own internal accuracy. So if it says we think the GPS is accurate only to 1 meter, call it, because they always talk in meters and not feet, then it's usually pretty good. But the network correction services we have found considerably overestimate their accuracy. They say this is going to be accurate to 3 or 4 centimeters. And honestly, if you had a network correction service on a rod, it is because it can be accurate to that much because you can take a observation for 5 seconds or so. But when the drone is moving and kicking and flying at 30 feet per second, it's way, way, way overestimated on those network correction services. Part of why we don't like them. Again, please use a local base station of some form. DJI base station, like a lot of things DJI, stupid simple user interface, really easy workflow, not going to be the best tech specs on paper. You can use your existing equipment, but with the challenge being it's a little bit more complicated workflow. Either is totally fine with me, as long as you use a local base. Here are some of our best practices. Like I said, minimum of 3 per project if it's RTK, 5 for non-RTK, plus 1 GCP for additional flights. And using clearly marked targets is really important. As a photogrammetrist myself, I really like clear targets, especially because I wasn't out in the field with you when flying it. So when marking ground control, there are a couple examples of what we think are non-ideal ones. Something like this, where it's just an all-white, single-color square, the exact center is not entirely obvious. Saying corner of concrete, a visual ID point or something like that. It's hard to find exactly, is it this corner, is it that corner, which corner is actually challenging to pick out specifically from the drone. Chevrons are another weird one that I've learned to really hate chevrons, because some surveyors mark the front tip there, some mark the inside corner, some mark a point between the inside corner and the front tip, and every surveyor thinks that their way is the only way to do it. Or, this was my favorite one. That was a real project that someone set in. I don't know what happened. So honestly, if you want to mark your control like that, please do. That made my day. No, our favorite is just simple checkerboard pattern. You can buy things like this on Amazon. Those ones are very, very easy to identify. I'm also a sucker, you know, shameless plug. We actually make and sell these. Everything's in black and white because photogrammetry used to be in black and white and the high contrast was there. Now that the entire world is in color, having super bright pink and green is so much easier to pick out from the air. So that's our preference, at least. But it doesn't have to be that. It can be literally any target, but the checkerboard pattern is very much what we recommend. So another question that often comes to me with ground control is, well, I've got this ground control, I've got this base station, I've got this great LiDAR rig. My dealer told me that I can do a survey with no control whatsoever. And that is technically true. The technology is there that you can do a survey without any control, without anything on the ground. However, we think that that is an irresponsible thing as a land surveyor, both because you might submit bad data and might not have any way to know it, and because it's often super complicated and expensive to validate with that level of precision and reliability that you got it right. So we think that, well, no control is not good enough for a surveyor. If it actually is going to be for a survey, you need control because it provides a check on the data for all of the so many human errors that can happen. Whether you set your datum wrong, whether you had two crews that were shooting different parts and they had slightly different setups, or they set their rod height wrong, or something happened. There's so many things so many mistakes in data translation and processing that can happen that not having control, we think, is an irresponsible way to do it. If we want to get technical, we don't always use the control as the control. You can set control and use it exclusively as check shots to validate your data, not to control your data, and that's totally fine. But having ground truthing data is very, very important. We think that it should be necessary for actual land surveyors. It also helps for localizing a project. We work with a lot of projects that need to be localized. They might be approximately NAT 83 or not exactly. Some were shot and they're on a 5,000 by 5,000 grid. Cool. We don't care about that because we localize with ground control, so that's no issue. This is another thing that's bigger for me coming from California. It's seismically active there. The ground moves by a couple of tenths of a foot every single year. So if you want to actually have it match up with other boundary or prior surveys, you have to localize it to a job site. So that's something that's very common with us and part of why we really, really like having control and think that some level of ground data is necessary, even with RTK, even with PPK, even with all of that. The cost of having a perfectly reliable, no ground data workflow is exceptional, and the risks are very high as well. So we don't like doing no ground control. All right, and we're getting into the office workflow, and a little bit early for the break, but this is going to be a great time for us to just take a 15-minute break. So go out, get a drink, get a snack, use the restroom, and I will see everyone at 2:25. Come on back in. I'll get everything started while everyone's still filtering in, because I've actually got a whole lot of stuff to still cover. I don't know if you've been able to tell just from my speaking up here, but I actually really like this stuff, and for better or worse, I could talk about this for 6 hours about all of the technical nuance of drone data processing and GPS and LiDAR, but I don't think anybody wants to hear me talk for 6 hours straight, even my wife. So instead, you got 1 more hour of me, and we're talking about office software and all of that stuff, and that side of the drone workflow for actually getting from flying a drone to then to then getting it into CAD, getting those final survey deliverables, keeping your clients happy, and having a good workflow. All right. So the office processing workflow is itself a couple of steps. This is all about that predefined workflow to getting from flying a drone to a final survey deliverable in a way that is repeatable, efficient, and useful. And that has a couple of different steps, which we will go through every single one of these in as much detail as time allows. So step one is going to be point cloud processing. That is, like I've mentioned before, the process of photogrammetry, which is stitching the images together into a point cloud or an orthophoto, as well as LiDAR processing as well. That's creating those full resolution, big file deliverables. Accuracy verification, taking those big files, making sure that they are exactly what you want. That's where all of that control that we were talking about and check shots came in. Making sure that if you draft survey deliverables on this, that it actually is accurate, that it lines up with your other projects, and that it is the quality that you want. Line work drafting, that's the old tedious part of actually going from a point cloud into what your deliverables are. That means instead of a 1 gigabyte point cloud, you actually have a line for where the curb is with metadata on the layer that says curb, top of curb, back of curb, things like that. And then CAD integration is where you put it all together. That's where you put in your imagery in the backing, your tin surface, you merge in all of your ground data, you merge in your boundary data, you run your final QAs, put your symbols on it, print it, seal it, send it out. That's gonna be your last step there. So photogrammetry processing is kind of step one in this. That is where you start with the photos, the ground control, and RTK data if you have it, and it creates a, sorry, it's cut off there a little bit, a point cloud, an orthophoto, and a digital surface model. These are the typical outputs of photogrammetry for surveying. Can you make other outputs? Absolutely yes, but these are typically the ones that are actually useful for photogrammetric mapping and surveying. There's also LiDAR processing, creating that point cloud, merging it with your IMU and GPS data, classifying it, creating a digital elevation model, and converting your LiDAR data into useful formats. One thing that you'll hear me talk about a lot is, so many people think that the point cloud is a final deliverable. And I have never met anyone who actually likes working in point clouds or for whom a 200 gigabyte point cloud actually is a final deliverable itself. You usually want to get somewhere from that. You want to turn it into topo. You want to turn it into mapping the sag of power lines or where the poles are, where the buildings are. To me, those are intermediate file formats to be in that point cloud because they're just so huge and cumbersome as to be almost useless. Not entirely, but they're not great. So that's why you have to use drafting. This is that stage where you're reducing all of this huge, rich, every leaf on the tree data into something a lot smaller, a lot more easy to use, a lot simpler, and in my opinion, a heck of a lot superior, where you have a clean tin surface like would be demonstrated here, but lines for the curbs, you have your catch basins and drains, manholes, water valves, all of that, all marked, all classified. That is what the line work drafting phase is. It's extracting all of that data from those rich deliverables to reduce it to CAD compatibility, which again, Civil 3D, if anyone's ever tried to put a full resolution orthophoto or point cloud into Civil 3D, I mean, it just gives up and quits. So you got to do something in between. And then, like I said, finishing it into CAD, merging your field shots, creating a tin surface, turning that tin surface into contours, things like that. So just to kind of summarize what this process looks like before we start digging into the detail of each individual step, because this workflow is fairly important. So you start with photos, ground control data, and GPS data, RTK or PPK. That goes through the photogrammetry and LiDAR processing step. What that spits out is an orthophoto, a DSM or digital surface model, and a point cloud. You run that through the line work drafting step, which will spit out things like 3D points that you've extracted, maybe some polylines, typically in a DXF style file format. Run that through the CAD finishing step, and that will get you your final deliverable, including a tin surface, contours, site culture, things like street names, for example, in your DWG format. So this is kind of what the office office processing workflow these discrete steps actually look like. And I say discrete steps because at least the way that we process data, when we process project data, it is a very discrete step. It is in photogrammetry. It does not go into line work drafting until we have checked off that it has completed photogrammetry processing. It is not that we kind of do all of this at once and maybe mush it all together. No, no, no. A project goes through a linear step. We don't start line work drafting until we are confident in the accuracy of it, because otherwise that leads to rework, extensive costs, field revisits, all of that sort of stuff. This is the type of structure that a really good drone program needs to get reliable data out of it. All right, so now let's start by diving into photogrammetry. Photogrammetry, this is also my specialty. I'm a certified photogrammetrist too, and so this is what I actually work in a lot. But photogrammetry is definitionally the art and science of making measurements from photographs. Put it a little more simply, you take 2D pictures, you make a 3D model out of it. That's what photogrammetry is. Photogrammetry has obviously come a really long way over its history, but it's been around forever. The earliest photogrammetry was actually done, I think, in World War I, where they sent up balloons, took photos on black and white film, and tried to use it to create a map of the hills that they could use for artillery sighting in World War I. So this is not a new technology. The actual mathematical principles of photogrammetry were developed in the 40s and 50s and have been around often with, again, usually military applications really early on. And then it turned into commercial processing in the 60s, 70s, and 80s. Aerial photogrammetrists were flying around, taking these big metrically calibrated cameras, mapping them on Kelch plotters. And now we're into the era of digital photogrammetry, where you take thousands or tens of thousands of digital photos, throw them into a computer, and it maps hundreds of millions, if not billions, of individual points and matches across all of these photos. The technology has changed wildly from a guy with a black and white picture in a balloon to the computers that we use today, but the basic principles are exactly the same. You are matching the same point from two different photos and using it to create a three-dimensional map of the terrain. The core technology, the core way that this all works is totally unchanged, which is great because it's so well proven too. I mean, again, aerial surveying has been around for a very long time. Drone surveying is sometimes like the new thing. It's not the new thing. It's aerial surveying. Did I go? I might go off. Let's see what happened here. Try and reset that. Okay, I'll use that one. Cool. Sorry, technical difficulties. All right. There we go, I'll use this. So yeah, photogrammetry has been around forever, and even aerial, like land surveying with photogrammetry has been around forever. But photogrammetry takes an awful lot of time. It takes a little bit of human time to mark your ground control points, set up your initial parameters, processing parameters, but a lot of computer time. Once you actually send something to a computer, larger projects can take easily hours and often multiple days to actually finish processing. And then when they finish processing, if you only find out after the fact that you made an error, that you just typed one number in wrong, that your initial camera parameters were wrong, your accuracies, there's so many things you can do that, you know, it just takes time, and it slows the whole process down a lot. And improved computer hardware only does so much. I'll talk about computer hardware in a little bit for those of you wondering what computers I recommend, what computers we use, things like that. So our photogrammetry principles are honestly, number one, work smarter, not harder. We use an iterative process for all of ours where we start by processing smaller batches of photos in very low resolution because it can be done extremely quickly, and then we scale up to bigger sites of the project, putting it all together, higher resolutions, higher accuracies, to actually get all of the bigger problems out of the way early, right? Any big blunders that might be from low overlap or a badly shot control target or anything that might have happened of the hundreds of issues, forgetting to take a lens cap off or having mud on the camera. We've seen all kinds of things. Okay with this. But also for us, having a human in the loop is really important to our principles, at least how we view things. There are a lot of softwares out there, Drone Deploy being the most popular, where you can just upload photos, it processes photogrammetry and spits out a map. And I actually really love Drone Deploy. I know a lot of the guys that work there. They're a great company for making maps, and quite frankly, they're really affordable and very fast. But they aren't always going to be up to survey grade because of what we need in terms of accuracy for actually delivering really high quality accuracy in a reliable manner. If you're just looking for a picture that can be off by a couple of feet as like a base map, go to Drone Deploy. They're going to be way cheaper than any of the other options that I'm going to talk about today. And that's why they're a great company, but they're just not meant for surveys. For surveys, it takes a little bit more time to get that accuracy, reliability, and that sort of stuff. And that's why we always think there needs to be a human in the loop. I don't like black box cloud software. I love technology. I love software. We use a lot of it, but you need to actually be able to have a person there validating that it all works. For managing processing time as well in the photogrammetry step, honestly, a huge amount of this is decided in the field with mission planning. If you are struggling with processing and you're saying, photogrammetry is taking me days, there are all of these errors, it doesn't come out right, there's a better than even money chance that the solution is not in your software or computer or even office workflow, but it's actually in your mission planning for how you collected that data. That's why I was talking so much about it. That's why half of this presentation was about this mission planning stuff, is because that really does drive these photogrammetry errors. And that's why I can say, if you follow my advice from the first half, you're already going to be better at data processing without me having talked at all about data processing yet. Again, with some of those other themes, there is such a thing as too much data. You will also find processing time is nonlinear. If you double the amount of photos, it typically quadruples the amount of processing time that it takes. And so as far as solution goes, a good workflow is worth much more than a good computer. This goes back to that whole don't spend money on the things you don't need. A lot of people say, this photogrammetry is taken, it's going to take 24 hours for this thing to process. I need a new computer. You might, but there's a good chance that you would save more time with a good workflow. Because a brand new computer, the difference between a 2 or 3 year old, reasonably good desktop computer and a brand new cutting edge one, that might shave 10 or 20% off your processing time. Take something that took 8 hours and then it takes 7 hours, which doesn't really make that much of a difference because it's basically overnight anyway. Or if you have a good workflow, it can take something that might take 8 hours and have it take 2 hours instead. And that's why I'm a big fan of workflows instead of computers. And again, I say that as a total hardware geek that builds his own computers for fun, but that's not really a money-making venture for me. Don't buy computers from me, I promise you that. That said, these are the computers that we use in our photogrammetry processing. We process data from all over the country. And what you will notice if you're familiar with computers is that this is a high-end but not insane level of computer. It's about a $4,000 computer or something is once you spec it all out properly. But you can spend a lot more money than that. There are workstation vendors out there that'll try and sell you $20,000 computers. And are they going to be faster than this? Yeah, by about 10%. So you can spend 5 times as much money for a 10% faster computer. What we've actually found is if you need more processing power than this, buy another one, and then another one after that. And having multiple computers running in parallel with the right workflow, multiple computers and multiple servers in parallel is far, 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 far faster than a single, Xeon grade, whatever NVIDIA's latest $15,000 processing chip is. Workflow makes all the difference as far as computer hardware goes. There are also different options for how you process your photogrammetry from a business perspective. Number one is your automated cloud-based processing. That's the Drone Deploy thing that I told you about, or any of the other cloud solutions out there. They are typically going to be the most affordable. They are going to be the fastest in terms of their turnaround time and extremely scalable. With the downsides being typically they have low accuracy, which makes it a non-starter for a lot of survey applications, and either no or low support, which is fine depending on what you need. There's also local software processing. That's where you buy your own copy of Pix4D, you buy your own computer, you hire a photogrammetrist, or you have your drone guy or whoever's the tech guy in your office learn surveying software. That has the challenges though, or it's definitely the most customizable and you keep the most control. But the downside of that is that it's going to be typically the most expensive and there's a pretty long learning curve. There's a reason why to be a certified photogrammetrist, you need 6 years of experience in photogrammetry to actually get your cert. It's a PhD level science to actually be on that far end of photogrammetry. Or work for an outsourced photogrammetrist. That is something like me. This is what I do. This is what our company does. Where it's most flexible, no learning curve, highest accuracy, with the downside being, it's not all upside, right? The downside being, it does typically take a little bit more time and it can be a little bit more cost effective or a little bit more expensive than anything else. But there are different options for processing out there, and there are companies that use any one of these ones successfully. So I'm not actually trying to tell you which one to use, but you should probably work with me. Anyway, that's beside the point. Using photogrammetry software correctly. This is another one. Pix4D is the market leader in drone photogrammetry software. That is actually the primary software that we use as well. It is a great software, and it is perfectly capable of very good results. And people say, oh, great. So what settings do you use to get good data out? And the answer is, it is not about the settings. There is no one setting, there is no one thing that you can do that will work on all projects. Projects are different, drones are different, the weather is different, the real world is different in terms of how different constraints can impact a project. I remember seeing projects where they were doing a survey of a person who really didn't want to let anyone on their property, and so that we had to find a way to survey it without setting control. Actually, there's another one that we're talking to someone who's trying to survey a old World War II era munitions site where there's unexploded ordnance in the ground, so they can't send anyone out. And I'm like, all right, well, that means I can't tell you to set some control points right over there, because if there's unexploded bombs, you don't want to go jamming your rod into the ground. But having the right workflow to be able to kind of know what a good photogrammetry project looks like and go through that, that's going to be what's really, really important. So other photogrammetry softwares are out there. They work too. Software, that'll be another one of those themes that you'll hear me say a lot over the next hour. There is no magic bullet software. Everyone wants to come to a presentation like this, say, I've got the secret. I've got the secret that everyone came here to know, and it's this software. You go to this website and all of your problems will go away. And I wish it were that way. That's just not the way that the world works, because if there was such a magic software, there's a good chance you would have already heard of it. Pix4D, Metashape, a handful of other softwares out there, Pix4D and Metashape are definitely the two market leaders, are all usable. Same thing with LiDAR processing and line work extraction. There are a lot of softwares out there that are usable, and none of them is a magic bullet, solve all of your problems at once. So let's talk about LiDAR processing now, because again, even though photogrammetry still makes up the bulk of drone surveying, LiDAR processing is what most people are interested in because it is the new thing, and also again because there's a lot more questions about LiDAR processing. Well, for starters, you need to actually turn the LiDAR data into a point cloud. See, the way that a laser scanner works is the LiDAR sensor itself only records the distance from the laser itself to the ground. It doesn't know where it is, it doesn't know what angle it's pointing at, it doesn't know any of that sort of thing. So in order to actually create a point cloud out of LiDAR data, you need to process the raw laser scanner data with information from the GPS or GNSS system, the IMU, an inertial measurement unit, any gimbal data, and often the imagery to colorize that point cloud before you can do anything else. This step is usually controlled by the manufacturer of the drone. They have their own proprietary software, proprietary workflow for combining all of that and getting it into a usable datum, the right coordinate system, and actually creating an LAS file, which is then going to be the input for the later on steps. So you combine all of that, can often look like these sorts of files. In DJI, it's done in the software called DJI Terra, which is their kind of LiDAR pre-processing, is what it's often called, to create that point cloud. Then, depending on your system, you need to align your swaths, or depending on where you set up and moved and how you set up your local base station, you need to make sure that each individual flight aligns with one another. Sometimes the raw data, when you come out, will look something like this. So making sure that you align your LiDAR both in X, Y, and Z is really important. Again, it really depends on exactly what LiDAR hardware you're using in terms of the exact workflow of how to do it. But the most important thing is just being aware that this is a problem, that things can move in any different direction, be different from swath to swath, and that you're actually running your QA on it. And the reason I say run QA is because if you just run this in, like, if you just assume your LiDAR data is good and throw this into a processing algorithm, it'll look at this and processing algorithms say, oh, well, the lowest one is going to be vegetation, or is going to be the ground. So it takes this green line as ground, and it calls this red and blue line vegetation, like shrubs or trees or something. When any human can look at that and say, no, 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 that's a roof, and that is the same roof on all three, it's just mismatched. Well, this is one of those things where computers are pretty dumb still in knowing that a human can look at that and say, those are three roofs that need to be aligned, and a robot would look at that and potentially say, huh, so I've got some ground, another ground, and then a lot of vegetation or an eave or something like that. It just doesn't know the difference. So being aware of that issue to make sure that you do process it is going to be pretty important. You also have to georeference it, localizing it to GCPs, ground control points. I talked a lot about setting GCPs. Localizing it is important too. It can be a little trickier with LiDAR data depending on the exact workflow you use. Some LiDAR, when it first comes out of the system, is going to be uncolorized. This was a fun one actually creating these slides because this is what a colorized photogrammetry point cloud looks like, and this is what the raw LiDAR point cloud looks like. And I actually spent the time to make sure that those are exactly the same place on the project, even though it doesn't matter at all because you can't see anything on the raw point cloud. There are other ways to do XY georeferencing on LiDAR data sets. You can use things like the intensity layer of a LiDAR point cloud to actually see X and Y, or you can compare it to known vertical points like the edge of a building or trees or things like that. But once again, it comes down to just having ground data to measure multiple points across the site to ensure that your accuracy is actually where you want it to be. Again, we really like using ground control points because they are simple, reliable, cheap, and verifiable. So many of the other methodologies that are out there are extremely technical in nature and are very cool, and they work great, but they're not reliable, and they won't catch themselves. You won't be able to see, oh, wow, that's 6 feet off, because you're just trusting that it works. I don't like just trusting that things work. I like verifying it, and that's why ground control points are so great. They let you verify your LiDAR data. I'm a big proponent of LiDAR. As far as georeferencing those point clouds, LiDAR hardware often relies exclusively on the GPS or GNSS system, and a lot of vendors really push that without any sort of ground control or ability to control. There absolutely are ways to georeference and validate data, both with check shots as well as with using them as control points. You can control LiDAR data to an arbitrary 5,000 by 5,000 datum, or localize it to a project. You absolutely can very easily, and we recommend it. So I don't buy that the arguments that LiDAR must be GPS processed only and can't use control. I found it again to be a much more reliable workflow for survey. So next up is going to be measuring and certifying accuracy. So we've created, that's kind of creating the point clouds, creating those raw, really large intermediate deliverables. So next up is, how do you know that it's actually accurate? And I've talked about accuracy, right? I've said you can get about 1/10 of a foot accuracy, maybe 2/10 here. But a really important question that I haven't asked, at least not out loud yet, is what do you mean by accuracy? Because there are a whole bunch of different definitions. And to answer that question is there is no single definition of survey grade accuracy. There are different standards to measure accuracy. There's the National Map Accuracy Standards, which was commonly used among surveyors for many, many, many years. Very simple to understand, but it doesn't quite have the nuance of more computer and statistically based modern standards. There are confidence intervals. I want 95% of my shots to be within X feet or something like that. And even when I say survey grade, I say 1/10 of a foot, which a lot of people consider survey grade, but it depends on what you're doing a survey of. Again, if you are doing a railway survey, 1/10 of a foot might not be good enough. Or if you're the Department of the Interior and you're measuring 50,000 acres of rural Wyoming, then survey grade is 10 feet. And if you're in plus or minus 10 feet, you're great, and that's a survey. And that's actually survey grade because they know what their accuracy is for the needs of the project. So this is why if you ever hear someone say survey grade accuracy, you should probably raise an eyebrow and say, what do you mean by survey grade? What actually is, how are you measuring that? You can also use just other things, the RMSE or root mean squared error of the ground control points. This is one that's used on the Pix4D quality report, which means that a lot of people have heard of it, where you put in 6 ground control points and it says, great, you have an RMSE error of your GCPs at 0.003 of a foot. And if that makes you raise an eyebrow, it should. You don't have 0.003 of a foot accuracy on photogrammetry because that's not a true accuracy standard as far as measuring a ground control point to itself. You need to use independent check shots. So that's where the best measure is the RMSE of independent check shots. For anyone that's a statistical, there we go. I'll go out of order a little bit. For anyone that's a statistical geek like me, the gold standard of actual academic measurement and certification of accuracy is something called the ASPRS Positional Accuracy Standards. ASPRS is the American Society for Photogrammetry and Remote Sensing. It's a nonprofit organization that puts together a lot of really, really good resources. We're members. If you're looking to ever become a photogrammetrist, check out the ASPRS. They are a really great organization. My only criticism of them is that they are extremely academic. They care so much about intellectual and scientific rigor so that when you actually certify accuracy, when I say this conforms to, an accuracy class of 0.3 of a foot as measured by the ASPRS positional accuracy standards, that means you're following all of these procedures to actually really, really validate your accuracy against all known forms of error. So if you want to read through it, this is completely the gold standard of measuring and certifying accuracy. It was published in 2014. They're actually going through an update right now that I think is set to come out later this year of updated measures that brings in a lot more kind of drone work too, which is very, very cool. Because, among some of the topics that are covered are things like accuracy versus precision, sometimes called global accuracy versus relative accuracy or things like that. Accuracy meaning how kind of tight things are, Precision is how close things are relative to one another, so relative accuracy, whereas accuracy is how close it is on a global level. This might mean, hey, all of your shots are measured perfectly, but every single one of them is shifted up by 1 foot. That would be something that is going to have high precision but low accuracy. And knowing the difference there is really important because it depends on what you need. Knowing things like systemic bias if your GCPs might be all shifted by a single amount. LiDAR has a couple of different ways that are important for checking and validating accuracy. They'll still all come up in the ASPRS positional accuracy standards, but just being aware of things like swath-to-swath accuracy, where certain swaths, when they get further away at higher angles from the LiDAR unit, is going to have a larger spread and more accuracy. This rainbow mess of colors actually means something to someone that does a lot of LiDAR data processing, where the colorization is by the LiDAR scan angle, and at high scan angles, you're seeing significantly higher deviation from the mean. So that's these red lines. The further you get away from the center underneath the drone, on some applications, if your LiDAR unit isn't calibrated, can create error in that way. Different ways of checking for error in that error checking step. Because error can be caused, it can be caused by so many things. Moving vehicles, storm grates cause weird things where some LiDAR data can come back from underneath, from inside of sewers, reflective surfaces. There are a lot of different sources of accuracy, and that's why these positional accuracy standards is really the gold standard. It's super academically rigorous to make sure that when you say, you're the surveyor, it's your job to actually give a thumbs up and say, yep, data's good. Why? Because I promise you I've done it right 100 times, and I can back it up if you need me to, but yes, the data's good. These are what some of the certification statements actually look like right now. These are some of the ones that are also going to change in the new standards, which is cool. So that's accuracy. Accuracy is really important. ASPRS is a really, really great organization. So let's talk about point cloud classification next. Point cloud classification is actually taking this point cloud that's going to be colorized, have elevation, have all sorts of things, and turning it into individual classes. That's a building, that's a tree, that's a power pole, that's a power line, that sort of thing. The first step in point cloud classification is to ask yourself if you actually need to do point cloud classification at all. And for a lot of projects, you might not need to. There might be better ways to simply extract the features. And also ask yourself what type of classes you actually need to split things into. For the majority of projects, when you're working with LiDAR data, there are only two classes that you actually care about: ground and not ground. And everything else you can ignore, because usually you're just doing a topo when you're working with the LiDAR data. So that means taking the time to identify the difference between a fence and a building and a bush doesn't matter because they're all not ground. So ask yourself if you even need to do it. There are automatic classification algorithms out there, and I'll be honest, this is one of the more exciting areas of LiDAR processing and data processing, because these ones are actually rapidly advancing. They still create a lot of errors, both false positives and false negatives. But this one's pretty cool in that it's rapidly advancing, and it's a good starting point to LiDAR processing. Start with an automatic classification routine, and then go in and manually clean it up. The better that these classification routines get, the less manual cleanup you have to do, and that's just a win-win there. So those are pretty cool. But yeah, asking what classes you really need is important, whether it's ground, roads, bridges, noise, vegetation, power lines, that sort of thing. Obviously, there are circumstances in which you need to classify a ton of different things. You need to classify the transmission lines versus the distribution lines versus the shield wires. And you need to export it into PLS CAD, for example. If you're working in PLS CAD and actually doing a power line survey, then yeah, you totally need to do all of those classifications. If you are doing topo underneath the woods, you do not care about high veg versus medium and low veg. That probably is not a good use of your time, or anything like that. So asking yourself what classes you really need is probably the most important part of the workflow. This is one of the more interesting slides is, okay, so what software do you use? What softwares are out there? I'm having a heck of a time classifying my LiDAR data. What can I do? And I'm here to unfortunately tell you there's not a lot. I know people that use all of these successfully, and I know people that hate every single one of these individually. And I can tell you that I'm familiar with all of them and have used some of them very extensively. There is no one great one. My recommendation for LiDAR software is use the one that you're most familiar with. Because you might say, oh, well, the ground classification algorithm sucks on this one, but this one takes a lot of time and really struggles with point clouds of more than 100 million points, and on and on and on. And the answer is, yeah, none of them is perfect at everything. They're all kind of a bit of a pain, but they have pretty long learning curves. So if you are an absolute Trimble Business Center diehard, cool, go for it. If you love the MicroStation ecosystem and you want to put TerraSolid, which is a MicroStation extension thing, great. TerraSolid's a really good software as well. If you like Global Mapper because you do GIS work and you have a couple licenses already, awesome. Global Mapper is great too. They all have their trade-offs. There's really no magic bullet, unfortunately. LiDAR processing just takes time, experience, and skill, and the more you do it, the better you get at it, but there's no magic bullet. So sorry if I'm letting anyone down on that front. There's some other questions in LiDAR processing, regardless of which software that you use, that's really important. One of them is whether or not you should thin your point clouds. When drones fly with LiDAR units that have such high bit rates, they gather so much data, that it's not crazy to have LiDAR clouds in excess of 1 billion points. Those are huge, really cumbersome to work with, big files, pain in the butt to process, import, export, move, whatever. So a lot of people want to thin them, and that means there are different ways of thinning it, excuse me, to actually take the point cloud and make it a little bit smaller. This is another one where there's no industry consensus on this yet of what the exact best process is, which is part of why it's one of those things that is interesting to me, because there are different ways to thin a point cloud. You could either do what I often call dumb decimation, which is where you take a point and you just pick every 10th point completely at random. And so you're just decimating the point cloud, you're reducing the size by 90% and just making everything thin. That actually has a lot of statistical benefit to it because it's very simple. You're not introducing any new biases into the data, but you're losing a lot of the resolution. If you're doing power lines that might only have a few points, you're getting rid of a lot of those points. If you have sharp curb lines, all of a sudden they become a lot less sharp. There are also these more advanced methodologies that take denser areas like in trees and try and thin those more aggressively, but then in areas where it's thin, that doesn't thin it as aggressively. Those are really cool and sound smart until you really look into the data and see that that can introduce biases into the data where it takes a nice surface and can actually split it into the high and low points and create a kind of dual terrain. So there are different, thinning point clouds is something that I would say, being honest, is used sparingly at this point because there's a lot of pitfalls there which are not all super well documented and takes a good amount of experience to make sure that you're thinning a point cloud in the proper way. Then is classifying and filtering your points. That's things, like I said, removing vegetation. This is actually an interesting point cloud. This is one where we ran it through an automatic classification algorithm, and you can see it did pretty good. The ground is mostly in brown. There is some green vegetation there that it must have thought was grass. Some of these gray and orange points are a little weird. I think those orange points it thought were power lines going through, but were almost for sure going to be noise in this particular case. But you'll also notice there are still gaps. There's gaps in all data. None of this data is perfect. No, there is no LiDAR unit, by the way, that can penetrate all vegetation perfectly and just get you the ground. There is absolutely dense enough foliage out there, especially with all kinds of like vines or really dense tree cover in the summer months that LiDAR is not going to be able to penetrate. Make sure you're aware of that because once again, this is one of those things. Any human can look at this and easily interpolate and say, yeah, there's a surface under there. Extracting that, like I said, you classify everything, and typically our methodology is to take the LiDAR data or the point cloud data and then convert it into a digital elevation model. And that means we're taking what is a point cloud or a vector data set and turning it into raster data, which I think is on here. I'll talk about that in a second. Let's talk about more things of why we like human in the loop, is answering the question of what is ground. That sounds really obvious. This is the ground, right? Turns out it's not so obvious. There's a debris pile on the site. Does that count as ground? Well, it kind of depends. How big is the debris pile? What are they trying to do with it? Are they trying to figure out volumetrics of the debris pile so they can move it away? Or is it going to be moved by a construction site next week, so ignore it and you should draw the surface underneath? Same thing with stockpile measurements. Is the stockpile itself the ground, or do you interpolate a surface underneath so that you can create volumes? Or for rock outcroppings, is the rock the ground, or do you make a ground and then you mark the rocks for a different purpose? These are all kind of site dependent and something that humans are typically pretty good at. And also, so yeah, those are some of the things where just deciding exactly what is ground winds up being a little bit trickier than just a simple mathematical calculation. And let's see, do I have a picture? Oh yeah, if these were under trees, could you tell what it is? That's another really interesting one because a human can pretty easily see sometimes if there is a car parked under a tree. We look at it, and from the LiDAR's standpoint, it looks kind of like a stockpile, kind of like just a hill. But a human can see the profile of a car so easily that even without imagery, when it's through the trees, you can see that it's clearly a car. It's a temporary object and should be completely disregarded from the final mapping, or at most it should be mapped as a separate object that there was something there. But typically, like a car is easy for a human to disregard, but a computer can't tell the difference between a car and a pile of rocks like a human can, at least not yet. So next up then is rasterizing the point cloud data too. And this actually applies both to photogrammetry and LiDAR as well. This is not just a LiDAR thing at this step. Point clouds, they are called clouds. They are not a perfect set of points. They have some noise to them. Aerial LiDAR point clouds, even in perfect scenarios, have noise. So you can't quite tell in the imagery up there, but that's going to be a road, and this is the cross section of the road. So that is asphalt. Asphalt is hard. If you had perfect LiDAR, or honestly, if you had ground-based LiDAR that wasn't subject to the same noise as aerial LiDAR, you would see one really, really thin, perfect line of points as it kind of goes down. That's into the gutter area, and that's up towards the crown of the road. But what you can see is there's this noise. It's a spread. It's a cloud. And the size of that cloud is actually like half a foot. It's kind of a lot. And that means that each individual point that comes out of a LiDAR system itself should not be relied on because there is noise. However, the statistical average of this, if you look and were to draw a line kind of through the center of that cloud, the statistical average of those points is going to be overwhelmingly more accurate than the point itself. This is a really cool technique that can be used so that the actual final survey data is more accurate than the sensor itself. And this is proven out by lots of studies that actually show, and same thing with photogrammetry, your photogrammetric map might have some noise to it, but if you take the statistical average, you can even get, sometimes you can get accuracy that is better than the resolution of the imagery, which is a cool thing that you can do with this sort of interpolation. So to do this, how do we actually make that process? Well, you take vector data, which is LiDAR data, point clouds, and this is what like a vector data would look like, kind of angles, and you turn it into raster data. This is turning it into like a picture or a map, what you're used to looking at, where everything is broken down into pixels. So the way to do that is kind of like this. You take a statistical average of your vector data and you turn it into raster data. Now this looks ugly, and because it's super zoomed in, you say, well, this looks so much nicer. And yeah, that's true, but it's more just to illustrate the point of what it means to actually bin things into these pixels. And when you do that, here's what another surface actually looks like. Here we're talking in, this is in profile again. There are a couple of points here in brown and some vegetated points that are up here on top in green. And these are the points. You see there's a lot of kind of noise here. And depending on exactly what type of algorithm you use to average these points out, what your bin size is, which ones you include and exclude, you can have some of these that are kind of choppy, but then you can see this one at the bottom. When you actually dial in your settings right, you have that much smoother surface. And what you will find, like I mentioned, that smooth surface is going to be way more accurate than any one LiDAR point. When processing LiDAR, you shouldn't just extract individual points, even with photogrammetry, I believe, actually, too. It's not great to extract individual points because those individual points aren't super reliable, or at least not as reliable as when you rasterize data like this, create a smoother surface. This is especially easy to do because drone LiDAR has such ridiculously dense data, thousands of points per meter in terms of its density, as opposed to like a state-provided aerial LiDAR, which is going to be a much more granular, much lower resolution product. And that's how you can turn something like this, wooded forests, into something like this, where you can clearly see the exact banks of the stream. You can see the tire ruts from where a truck was driving underneath the trees. You can see fallen logs, because that is how good this is through the trees when you actually rasterize this data and get a good surface out of it. All right, so we got about 15 minutes to go, so now let's talk about one of the last steps, which is going to be line work drafting. So what is line work drafting? As I mentioned, that's when you reduce all of this rich data, even that last photo there, this is still a ton of detail, and this is still gonna be a pretty big file. We've taken it from maybe hundreds of gigabytes now to at least hundreds of megabytes, but it's still kind of a pain in the butt to use. So line work drafting is going to be extracting all of these features, curb lines, planimetrics, all of that good stuff. Why is it necessary? Well, because the files are too big. Full resolution ortho photos are huge. You can't attach that to an email like you can a CAD file. And it has too much data you don't need and not enough data you do need. Automated contours on any of the raw data often looks like this. Some areas it's good, and then it'll try and draw contours around random stuff. It gets super jaggedy and again blows your file sizes up huge as well. One of the first questions when you're doing LiDAR or when you're doing line work drafting is if you have flown a site with a dual photogrammetry LiDAR drone, which again we like, is picking which one you should use. This shows kind of some of the spread that on hardscape, that kind of darker line is going to be photogrammetrically derived. The yellow dots are going to be LiDAR derived. Photogrammetry remains more accurate on hardscape than LiDAR for aerial LiDAR. So integrating a mixed workflow where you actually extract hardscape data from the photogrammetry and the imagery, and then the topo data from the LiDAR, or topo data in vegetated areas from the LiDAR, that's one of the most effective workflows to use, is actually a blended workflow. Because there are other things, I mean, even with, take paint striping, for example, just in a parking lot. If you're doing an Alta survey and you need your paint striping, pulling that out of a point cloud is actually kind of hard because visualizing, seeing where all the paint stripes are is difficult to do. Mapping that on an ortho photo or drafting that on the ortho photo directly is extremely easy to do, and it's really easy, again, for a human to say, oh, there's a car parked on top of this line, but I can draw the line underneath it. It's really easy there. So blended workflow we think is really, really useful and probably the top tier approach for LiDAR mapping. Is not exclusively LiDAR mapping, but using both. As far as your line work drafting software, this is going to be your same story as the LiDAR software. There's really no magic bullet. There are a bunch of different softwares out there. Some of them also do the kind of LiDAR processing as well, and they all just kind of take time. Quite frankly, they take very little computer time, so a little bit of the opposite from photogrammetry, but they take a lot of human time to draft it. And I'll point out, it's not super skilled labor that it's required. Photogrammetry is hard, takes a lot of experience and knowledge. Line work drafting is not. That should be some of the more junior people in your office, if I'm being honest, of, hey, here's a parking lot, draw all the paint stripes. You don't need to have 30 years of experience to draw paint stripes. But good QA and QC to actually check it is important because it is pretty human-based, this part of the process. So having someone to check, because humans make mistakes, that happens, but having the right procedures to actually quality check it can dramatically reduce any sort of errors like that. Like I mentioned, there is no magic solution though. Like photogrammetry, there are also different options for how you do this. There's automated software analysis that can automatically pick up curb lines and brake lines and all kinds of different things, or power poles or manholes. And those are getting a lot better, but right now they require an enormous amount of QA, QC, and typically aren't quite there. Sometimes, some applications they are. Again, this is another one of those places that's a really, really rapidly advancing field, which is really exciting to kind of monitor. In-house drafting is high accuracy, reliable known product. You control it, with the downside being that it's typically very expensive labor because either you're too busy, you have another job to do, or hiring people is tough, and it's super time consuming, or another shameless plug that you get from me, hiring a photogrammetrist firm like us that actually does this for a living, and this is what we are specialized in, but you then don't have the process control over it, of course, so always trade-offs in life. And it's important when doing this to even have a set of CAD drafting standards just to verify consistency too, from one project to the next, from one drafter to the next, to make sure that your curves have the right number of curb lines drawn, that your spacing between topo points is the same, that you know what to do of when to interpolate a line under a tree, or when to actually draw the cracks in cracked asphalt, and when to draw kind of the ideal where the sidewalk should be. All of that needs to be handled by things like drafting standards so that you can actually help. And I should point out, that's one of the benefits of having a drone fly it in the first place, is now every survey that you do, if you fly the drone, it has absolute real-time, not real-time, but up-to-date imagery of what the project site was like. So that if you look at the picture, you can turn off the imagery and say, okay, here is where the sidewalk is, or you turn the photo back on and say, wow, that sidewalk's in need of repair. Maybe that's important to the engineer for the job that they're doing. I don't know. Surveyor doesn't always know exactly what the project's going to be used for. But having standards is important. All right, and your last step in the process is going to be CAD finishing. And that's where you take all of this data that we've processed and turn it into this, turn it into a survey. And there are a couple of steps to do that, not too much. Number one is merging your photogrammetry and LiDAR data. If you did do what I recommend, extract some data from LiDAR, some from photogrammetry, it is in CAD all the way at the end of this process that those kind of finally meet up. If you did your accuracy verification, they'll meet up, and they will meet up very nicely. If you didn't do your accuracy verification, there's a chance that they don't meet up, and that would be a problem. But yeah, merging it all together in there. This is where you would also create a surface in CAD. Take all of the 3D points that you did, all of your break lines, create a tin surface, add in your contours, add in your labels, things like that. Adding in your custom layer templates, making sure it matches whatever the needs are of your client, or maybe you're working for the government and it needs to be exactly just so, getting your layers all set there. Improving visibility, a little bit more of the human touch things, right? Putting your symbols, your blocks, your arrows, so that a single point that might be your manhole actually becomes a symbol that looks like a manhole, things like that. And then adding in CAD-friendly imagery. I'll take an extra minute on this because it's another tricky one. If you've processed drone data, you know the full resolution orthophoto is massive and usually can't be imported into CAD whatsoever. You could just aggressively downsample it, and you're losing a lot of this good data that you've gotten before. Well, my advice, first of all, you should never extract your data from a program like Civil 3D because it can't handle the full resolution imagery. You always want to do your drafting. You want to draw those lines on a software that can use full resolution imagery. When you get it into CAD, there are a lot of really cool compression algorithms out there, whether it's ECW or Mr. SID or something like that, that can actually compress it so that it's less than 200 megabytes is usually about the Goldilocks limit for CAD we've found. Oftentimes smaller if we can get away with it, but trying to get it so that it's great for context, visibility, but still of a small enough size that it's reasonable to deal with, that you can share it with someone else, that you don't need an insane workstation just to open the file. Having that hugely improves usability of the final product. And it's optimized, it's great for context, for printing, for being able to see things like, you know, cracked curves, that sort of stuff. Because again, this is what your final deliverable should look like. It should look the same whether it was made conventionally or with a drone. All right, I'm sure you've heard me talk for enough, so I'll wrap things up and then let everyone go. So to go back to what I was saying before, I want to save you time and money. This is not about being the most technologically advanced person out there, because I leave that to NASA. This is about getting a drone program that you will use that saves you time and money. If you have a drone program that isn't saving you time and money, then you don't have a drone program, you have a research project. And I want you to have a drone program. That's what this is about, and that's what I hope that you guys can get out of this. And that means pick the right tool for the job. The drone is a wonderful tool. Drones can do so much in surveying, but they can't do everything, and they're not right for every single job. You also really should use a complete workflow. Take the 2 minutes for mission planning. Take the 2 minutes for accuracy verification. Those little steps right there, they're so small in the amount of time that they take, but so massive in the amount of time and headache that they can save you. And lastly, there are always companies like us at Aerotos where we are happy to help you. If you have any questions, want to see what we can do, feel free to shoot me an email, logan@aerotos.com. And lastly is if we have been recording this on video, I know the slides were dark. If you would like a copy of the slides and a copy of the video, shoot me an email right there, logan@aerotos.com. I'd be more than happy to send it to you. And with that, I'll stay up here for questions, but thank you so much for your time and attention.